So this is the chapter on PID programming, and it is it is a chapter in and of itself. I used to at one time have it in 2 chapters, and I just finally crunched it back to 1. It's long, and there's a lot here, but it's just one of many chapters that we talk about, and then we go on with life. But this is it's a good chapter because much of the programming that you can do in a factory has to do with process control as opposed to pieces and parts and starting and stopping of things. This is more of a continuous type, flow type programming, and in it you have, first of all, you have the old versus the new, and basically there's been an argument forever about DCS systems versus PLC systems for process control. Okay, and I'm not here trying to solve this issue for you. I'm just telling you that you're going to find some companies and some people that will argue that they need a DCS system, distributed control system, and these systems cost a lot more money than PLC systems do. But for various reasons, they like them and they're used to them, and they use them instead of PLCs. Typically, a DCS system is kind of the hub system, and around it there are various PLCs that do various other tasks. So a DCS system would be a DCS, and then various PLCs doing various subtasks. So you'd have PLCs communicating, and that would be the typical DCS system, okay? Now these cost a lot of money, but you get a lot of bang for your buck. The problem with DCS systems, in my opinion, is they do too much. They program a function for you that is pretty much fixed, and you have to basically take what they give you, and if you want to modify it or something like that, it sometimes is not easy to do. So they give you a lot of fixed functions that do a lot of good stuff, but basically, if you don't like what they do, you're kind of out of luck. PLC systems, on the other hand, are not as much money, but they let you do more programming, but yet there are caveats that you have to do in order to get things to work with a PLC system that these guys take care of for you. So these guys, they're not as much money, but they can communicate to other PLCs if you want to, but you don't have to. But if you're going out and competitively bidding, these guys usually win. But on the other hand, sometimes you get what you pay for, and sometimes these guys don't do the job as well because the person that's doing the programming doesn't know how to program the system, and they fall into some of the traps that are possible with a PLC system. So you're going to get arguments. You're going to get people that like this way and some people that like this way. I don't apologize for putting our eggs in this basket over here and saying we're going to do it this way, because we couldn't afford to have everybody have a DCS system. It just wouldn't work. And I don't think we can pick one system and it be the standard for all either. Now, dirty little secret is that the FBD, function block diagram, language of the DCS or of the PLC looks very similar to the language that is in the FBD looks very similar to that of the DCS. But the DCS has a lot of pre-programmed functions that allow you to do a lot of very sophisticated things very simply. So you can throw a lot in there and very quickly have it work. Okay. One of the things that is problematic with PLCs is the update of the data. So the data in and the data out has to be something that you take care of very well. And the general rule is if you're on a pulse and on a clock, and every clock cycle you execute your program and you get the data within 10% of when it's executed. So within 10% of the time that it takes to get it. In other words, the data is not back here, it's right in this little area right here. So you collect it, then you execute, then you're good. You collect it, you execute, and then you're good. You collect it, you execute it, and you're good. But if you collect data that is out here instead of close to the time that when you execute your program, your algorithms are degraded, okay? They don't work as well, and you won't get as good of a response in your program. And these guys take care of that. These guys do not. This is buyer beware. You have to do this on your own here. Over here, they do it for you. They guarantee you that this data is fresh. These guys do not nearly as much. So I'm not trying to say that these guys are always superior, but you have to be careful and you have to guard against the possibility of the data not being as fresh as it should be in order to get this to work. So what are we programming here? We're programming PID. We're programming a PID algorithm. And it's the same algorithm that you have when you're looking at a auto controls course, and most of you sometime have had an auto controls course. Tonight, this lecture is, and we'll probably go into Wednesday night as well for this, but we're talking about a PID algorithm that is a feedback algorithm that takes a signal in to a block, and there is a set point, and there is a feedback from our process. So there's an output, and then we go to a process of some kind. And then we get a feedback signal from that process that's a feedback. And that's our process variable, or our feedback from the process. Now, we can't always guarantee what this process is going to do. We don't know what it's going to do, but we do know that we can put an algorithm together that takes the difference between the SP minus PV, which is the error, and then we take a proportional term times the error plus an integral term times the error. Okay, this would be an integral term. This is 1 over t term plus a d term times the derivative of the error. And that gives us our output, okay? That's a simple, really not very sophisticated algorithm, but it works in a lot of cases. It works so well that most of the time, this is all you need. Now, this is not meant to model the process exactly, but most of the time you can find these three variables so that you can control the process and keep it stable. In other words, no matter what happens, you're going to be able to do what you want to do. Now, it's a one-eyed set point, or it's a one-eyed algorithm. In other words, you have one sensor coming back from this process. So if I'm having a PID algorithm in my head, and let's say I want to drive down the road, and I'm going to drive down the road, I only can have one eye open, okay? And I can't use the feeling of my body as part of this. The only thing I have to sense where I'm at is my eye, the one eye. So it's just one signal coming in. It's the process variable. And then you have a set point in your head as to where you want to drive down that road. You want to go drive a little bit to the left? You want to be right in the middle of the road? You want to drive a little bit to the right? Where do you want to drive in your lane? And you have to be able to then output by moving the steering wheel in order to do that. So that's a very simplified analogy of this. One eye moving the output with your hand on the steering wheel and trying to adjust to stay as close as you can to the middle of the road or to wherever your set point is. Now, if you hit a bump or there is wind or something else happens, what happens? Or if you want to turn around a corner, if you want to turn a corner, you change the set point, don't you? Or you might keep the same set point, but just have what we call a change in the load. In other words, you hit a bump, or you went into some gravel or something else, and you have to do something to augment that, okay? So you have to do whatever it takes to get back to your set point. All right, so that's kind of the gist of this. And the goal of this tonight is to, in a way, get you to the point where you can program a PID algorithm in order to get some labs done. And there are two basic labs, and we'll talk about both of them tonight, that you can do. And you don't have to do the whole thing. You just have to kind of finish them off, and I'll explain that to you when we get to that point. But this would be a very crude analogy to a flow, and this is a proportional only control. But basically, here you have a bellows, and you have a feedback device, and you have a device that manipulates up and down that actually opens and closes the flow through this this portion of this valve on this pipe. So if you move this fulcrum back and forth, you get more or less of a flow based on the amount of the bellows, based on the pressure of the bellows. Okay, so that's and by the way, this is proportional only, and you never get to zero error with the proportional only. You only get to a percentage of the error with proportional only. But you'll get something like this. You'll get something that looks like this as a response. But it's never to the set point. With just the proportional, it's never going to go straight to the set point. Integral control, it works kind of, but you need it with proportional. You need proportional and integral control. And most of the time, that'll get you most of the control that you need, P and I. But occasionally, you need the derivative as well. So the P, the I, and the D all together form a PID controller. And this is the equation. Okay. Now, this is the world's simplest PID control block. And this is one that I did use at one time. So this is a PLC PID. Now, what is coming in here? This is a variable that's coming in from the outside world, and you scale it, and then you run this PID block right here, and then you output the output from the output. Okay, so basically there is a set point that comes in that is not shown here, but in this block right here, there's a set point that's not shown, but you scale the input, you run it through the PID block, you get the output, and then you take the output and you set the output. So this is about as simple a PID program as you could get. This, by the way, does work. These three blocks for that program controller, this was the older version of the Allen Bradley. It does work because this is exactly how I did it. And another aside about this is that this gets into what we call instrument engineers. So instrument engineering, when I was at Owens Corning, there were three groups in electrical. There was the power group, there was the control group, and the instrument group. These guys did the PLCs, these guys did the PID controllers. And these guys handle power. They got it to the MCC, and from the MCC, we took it and made it run a process. So that's what I did. That's where I learned about PLCs, was right here. Anyway, so these guys, what they did was they bought the valves, They wrote the P and IDs drawings, and they made the process stuff work. Okay, they tuned the controllers. Right up to those PID controllers and did everything else. But they did that. As a result, when I left Owens Corning and I came to teach at the University of Toledo, I had never set up a PID loop. I had never tuned a PID loop. I didn't know spit about them, scared to death of them because they had always been kind of hands off because somebody else did them. And we would get into not big arguments, but we get into small arguments or whatever about how they did these, but they were the guys who did the drawings. Now, if you look at that book that I passed around, the drawings that are in the back of that book are P and ID drawings. That stands for Process and Instrumentation Drawing. P and ID stands for Process and Instrumentation Drawings. Okay? And how do you make a big P and ID? From a bunch of little P and IDs, which were basically the kind of thing that I just passed around. So if you want to know how to control something, you look at how somebody else did that something and you do it maybe similarly or whatever. Where's that book? Did it make it around, or is it still? Okay, does anybody else want to see it, or anybody else miss it or whatever? It's the LipTac book. If you want to look at it afterwards or whatever, it's here. But I'm going to tell a story about it a little bit later. But this is as good of a book on this subject as I find still. I don't know of anybody that you say, well, you get everything on the web. You don't get this stuff as well on the web. Book like this. This is a really, you say, maybe. With AI today, I don't know. But I think this is still probably hold its own as far as being able to find a P and ID on a specific process. So anyway, you pull out the P and ID from here, and it's like pull out what you want and add them, put them together, and you've got a P and ID for a whole system. Okay. So that's a specific type of drawing. Okay. It's called a P and ID. Okay. Later on in this chapter, I show you the symbology for the P and ID, and we really don't go through how to build it exactly, but you can from the lists I've got there, you can kind of see how a P and ID drawing is made, and that's about all I can say. Okay, so these are some of the ranges for the inputs and outputs for that card, for those various cards, and I'm going to skip that. But here, you notice that the output from the the scaled input now goes plopping into the process variable. So this output here is moved into the process variable. So you're looking at an analog signal that comes in as your feedback signal. It's called the process variable, or the PV, and there it goes. You move it right into that PV variable. And then the output, okay, and then the output moves from the process variable. You crank out your algorithm, and then the output is called the CV. So the input to the process is, here's your PID algorithm. Okay, here's your PID block. And this is a programmable block in your PLC. It's got a set point, it's got a process variable, and the output is called the what? CV. What is the CV control? The controlled variable. The controlled variable. Or control variable, one or the other. I don't know whether it's control or controlled, but anyway, CV stands for controlled variable, and that gets you the output. So in here, the magic or the whatever, the proportional plus integral plus derivative term, this is where you're doing all your calculations of the math is in there, okay? Now, it's not done continuously. It's done on a clock. So in case you are a theorist and you think, well, this is nothing more than the S domain, which is the Laplace domain, right? No, we're really talking about the Z domain. We're talking about the variables that are on a clock that are executed on a clock. They're not continuously executed, they're executed on a clock. Now, almost everything is executed this way today. If you were to execute continuously, what would you have to do? You'd have to build an electronic circuit, wouldn't you? You'd have to build a circuit that would do it electronically, or the old approach was to build this mechanically, a continuous algorithm that was continuously monitoring. But with today's technology, we typically run it on a clock. And are the PID variables the same with the clocked circuit versus the continuous circuit? Maybe, maybe not. But does everybody follow the difference between this and this? If you have a temperature controller, how often do you run the temperature control block? Temperature of a furnace. Once a minute. Okay, once a minute. If you have water flow, how often do you run the flow? Or how often do you run the clock? Once every 10th of a second, probably. Maybe once every 50th of a second, maybe, but in that range. Okay? What if you had you're running a drone and you're trying to control the PID algorithm? By the way, are there PID algorithms in a drone? How many of you have actually flown a drone and set up a drone? Are there PID blocks in drones? Yes. Yes, there are. Okay? So how often do those get upset or excited? About every millisecond, right? How often do those drone PID algorithms execute? Once a millisecond or thereabouts. Okay? I have a block that works with the ball in a tube, and with gravity you have to be very quick. But how often does that execute? Once every 10th of a second, or once every 100th of a second, or once every 10 milliseconds. So those are executed rather quickly on a clock, but they're executed this way as opposed to continuous. So again, not a big deal, but realize that this is not true Laplace. This is the Z version of the Laplace transform. If you wanted to know, that's what that is. Okay? So this is talking about wiring a current loop, and we're going to skip that because we don't have too many of these, but we're not going to worry about that right now. All right, and this is the old style PID instruction for the SLC processor. So there it is. There it is. Now here is the block for that processor. All right? The first word is all the various bits that you can set. And then there's other words down there that you can also set as well. So what are some of these things that you can set? What is AM? Is that in the morning? AM? No, that's auto manual. So a 1 is manual, a 0 is auto. What is CM? Again, probably have no idea, but I'll give you some of these, just a few of them. Some of these don't matter, but some of them really do matter. AM is the auto manual. CM is the what? It's either SP minus PV is equal to error, or it's PV minus SP is equal to error. Which is it? It isn't always obvious. So if your output takes off on you and goes to full on or to full off, what are you going to do? You missed it. You got the minus sign in the wrong spot, or you didn't, or you got it. So you flip the bit, you flip the CM bit. You see this? This is the kind of stuff that is part of this algorithm. And which way is it? You don't always know. But if it goes to full on or full off, you just flip the bit and it works. Takes off and works. All right? What about these words down here? What's SP, set point? What's about the K, the TI and the TD? Those are your three parameters that are what you would call your tuning parameters. So you have the KC, you have the gain, you have the reset, and you have the rate. This is the proportional. This is the proportional constant. This is the integral constant. And this is a derivative constant. All right, so there they are. Now, how do you find these? Did you look in a book? No. This is experience. Or you have a tuning algorithm, in which time you say auto-tune and push the button and it auto-tunes. So sometimes there's a program that finds these, and sometimes you have to find these yourself. There are folk that basically spend their whole lives doing nothing more than keeping track of these in their factory. And as the days change, as the season changes, and as the process changes, they change these numbers to optimize the way the process is running. Do you believe that? It's the truth. Especially in petroleum or refineries. In refineries, these variables can change, and they can be very critical to making of product. Okay, so if you don't get the right one today, it might mean because something else changed and you have to change this one to do something differently. And there are people that are very experienced that know what to do in certain examples, and they do that. And that's exactly how they get along in life. That's what they do all day. Now, I would not do that job for any amount of money they paid me. But there are folk that's what they do, and they like doing that, and it works out, and they make a lot of money at it because they make the company a lot of money. But just basically being able to change these three numbers to optimize the process that day is worth a lot of money. And they pay people that know how to do that. So they got a little black book, and they have notes on all kinds of situations, and they go around and they study what's going on, and by experience, and you say, well, AI should be able to take that job over. I don't know. I don't really want to get into that. But they are instrumentation engineers, that's what they do. Okay, so that gets you a little bit into this PID block. Now, the good thing about these kind of blocks is what? They let you play. So this is that block in the raw mode. In other words, here it is, and it lets you try. This is kind of like a running it and see how you can get it to go. And that's how this block works. So this is a setup screen. This is something you would never let an operator touch, but here's all your variables. There they are. Here's my control mode. E equals SP minus PV. You flip it, it's PV minus SP. Here, what is my mode? It's auto or it's manual, okay? In other words, here are some of my variables that I can set up. Here's my P, my I, and my D variables. There they are. This is the go fish stuff. Go fish. Find the variables that work. This is stuff you'll end up doing. Maybe. Hopefully. Okay. You won't be like me, who was 15 years out of college, about 20 years out of college, and I had never tuned a PID loop in my life. I never set one up, and a guy from Anderson's called me and said, "Can you help me set up a PID loop?" And I said, "Sure, for money I'll do anything." No, I didn't say that, but that's what I thought. But anyway, I got out there and I set it up, and it would not work. It was constantly not blowing up on me, but it was faulting. So what I kept doing was I kept raising the reset rate, this number, to as big as I thought I could get it. And it was slow, it was slower, it was slower, it was slower, and it didn't dawn on me to go the other way, make it a small number, because it's 1 over TI, which is the reciprocal. So the smaller the number, the faster it works, right? So I called a guy and he says, I think that variable is the reciprocal. Oh, so the smaller, the faster it works. He said, yes. So I made it 0.1 instead of 25. And guess what it did? Took right off and ran. So again, sometimes phone a friend is the best way to go. Sometimes knowing what you're doing. It always helps to know what you're doing. But the formula in some cases for this integral variable is the reciprocal. With Allen Bradley, it is. Which I didn't know, but now I do, okay? Now, these are controllers that are called single loop controllers. And you can buy these and put them in your control panel, and they work. And they do the job. Now, what's wrong with these? Is there anything wrong with these? Nothing wrong with them. They cost a lot of money, and you have to wire them together, or you can put it all into a PLC or a DCS and get around having to have all these separately. Now, when I first started working in industry, these looked a little different than they do today. They were really long and narrow, and they went into a card slot, like a card slot in a panel. And if you were looking at the side of the panel, the panel front would be like this, and these things would go way, way, way deep, and they would slide into a slot. They would go into a panel, and then you would have this, looking at this, would be looking at it from right there. But they were long, big, deep, long control panel devices. These aren't nearly as long or as deep as the old style ones. The old style ones, all this was electronic, was built in, and there were no microprocessors in those days. This was all done with discrete components. But now they're not, and they're not nearly as deep. But these things, you can have 2 or 3 controllers in one of these. These are going to cost you $500 to $1,000. As much as the PLC, these are going to be a very expensive way to go. But sometimes that's what people want, and these are what people buy. So in other words, this is the device, and this is called the faceplate. This is where the operator enters the variables, and where they see the output of it. And then the works are in a drawer. The stuff is back here that does all the execution of it. And then there's wiring on the back where you can actually wire up your SP or your PV and your output and let her rip, and this will work. But what about this? Well, if there's anything that goes wrong, you have to then basically wire something into this in order to say, hey, go to a lower mode or go to a manual mode. In other words, there's a wire on the back of this that says to go to a lower mode. So that's an aside about these guys. There's extra wiring that's got to be put into these. Any kind of thing you do with these, you've got to have extra wiring. Now, what are some of the things you can do on this screen? Well, I talked about mode. What are the modes? Well, there's auto and manual. In auto, you can have local auto, and you can also have what we call a remote or cascade mode. All right? There are other modes as well, but we'll talk about these modes in a second. Your set point is where you want it to go. The process variable is where it is. The output, or the CV, is the whatever it takes to get there. The error is the internal, what's the difference between the two. The deadband is kind of the slop of the system, may or may not be used. The gain, reset, and rate. Those are your P, the I, and the D. Now, you can also have a maintenance mode, but in manual, most of the time, you basically are running in a maintenance mode. Maintenance will allow you to get in and change things from the screen, but whereas most of the time you want to freeze the operator out so you can't work on on anything other than what you want him to work on. So here's the deal. What do you think operators want to do? Do you think they want to run in auto or run in local, or run in, excuse me, or they want to run in manual? Most operators want to run in manual. Is that the best system? No, it usually isn't. It's sloppy, and most of the time it doesn't get you where you want to go. Auto gets the algorithm into place, and it makes it so that it's working its best to get it to that algorithm, to get it to that set point. However, is it better to never program the manual mode? No, it's better to program it. I've had programs where I've actually said, here it is, and then because the operator was overusing the manual mode, the programmer that followed me took it out of the hands of the operator by doing what? They left the control, they left the logic alone, but they took the button off the screen. They put it in auto, took the button off the screen, and said, "Sorry, you can't put it in you can't use auto or manual anymore." Well, you can use manual because it's built in, but they can't use it because it's not on their screen. But this would be a typical how you would program an HMI screen for a PID algorithm. So here is my set point. Here's my process variable, and here's my output. Now these are bar graphs. Along the side are little tickle points that basically can move you up or down by 1 or 5%. So this moves you by 1%, this moves you 5% up, this moves you by 1% or 5% down. Same way with my output. Now if I'm in manual mode, I can control my output. If I'm in auto mode, I can control my set point. So this would be when I'm in auto mode, this would be when I'm in manual mode. Okay? And I also have entry points for all this stuff. So in other words, I don't have to use these tickle points, these triangles. I can set it up down here to actually put it to a value. I can set up my set point here if I want to. If I'm in local auto mode, I can put in a set point and it will take right here. Okay? Now, is there any way to not have a local set point mode? No, you have to have it. Why? Because when you're setting up your PID algorithm, even though you may run in a coordinated cascade system, in order to set this thing up, it's you crawl before you walk before you run, and you crawl in manual, then you walk in local auto, and then you run in cascade or remote. You may not have followed all that, but you need all three modes in order to set a system up. Manual, local auto, and cascade or remote auto. You need all three. Okay, so here are some of the things in the labs that we've had over the years. Now, I took this off the wall for the simple reason that you probably in 2350 wonder why we have these catch basins and all that kind of stuff. Well, originally when we moved over here, we had one of these on the wall in our old facility over at Scott Park, and it ran very, 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 very well. But when we came over here, they told us we had to go to the second floor, and there is a drain in these things that goes downstairs. It looks like it's going straight downstairs. It does not. It goes at an angle. This is a 3-inch pipe, but when you're running this full bore, it's 90 gallons per minute. That's a lot of water, and we can not fill this tub up, but we can get it pretty high. And when we first did it, the piping was such that it didn't go down well, even though it's a 3-inch drain, and so it flooded someplace else. It came out in another room. So they told us we had to stop that day. But they cleaned it up and everything worked for a while. And then a few years later, they got the bright idea to move the instrument air, the air supply, and they didn't move the dryer. So when you have instrument air coming in here on this pipe and it's not got a dryer in front of it, you can get condensate in this line like crazy. And it rusted it took this valve and it basically it got it bad. So one day we took this thing and we looked at it and we opened it up and there was water in it, and that was the end of that valve. So it took us a while. We rebuilt it finally. We got the money, we rebuilt it, and we put it back together again. And then we did this again. It flooded the basement. It flooded the first floor again. So we said enough, and we took this off the wall, and we basically discontinued this. It's a wonderful lab. One of the few labs where you can actually, I'll just give you the example. If you set up the P is equal to 0.4, the I to about 1, and the D to 0, it worked wonderfully. If you went above 0.8 or higher, this thing started to oscillate dramatically. It did like this. And it sounded like a drunken mule. It really did. It sounded, that wall shook and everything around it shook. So any little change, and even from 0.4 to 0.8, and this thing went unstable. You could hear the instability, you could see the instability, and it was dramatic. And I loved it because you could see when something would go unstable versus stable. So it was not a good day when we had to disassemble this thing and take it away, but we did. But there it is. Now, this is one of the other labs that we have, and this is one that you can use. Now, here with this one, this is the ball and tube lab, okay? So with the ball and tube lab, you can actually, and this is one that you can program. This is one that you can have access to, all right? So the ball and tube lab, there is a program for it over in another area. I'll show you where it's at. Okay, so it is at this facility. It is at hybridplc.org, and then courses, EET 4450, and then you see this one here, it's ball and tube program, lab 6, right there it is. So the ball and tube program under EET 4450 is valid, and you can take that program and you can use it. Now, how do you get credit for it? What's your end game, or how do you get credit for this? You have to build it. For any of these, all you have to do for either of these two labs is to build a faceplate. I purposefully in the program did not build a faceplate, so you have to add for either lab at the end of chapter 19, all you have to do is get it to run and build a faceplate. All you got to do. All right? Neither of the two that I have a faceplate, a real legitimate faceplate. And that's all you got to do is build a faceplate, and you're done. So add a screen, build a faceplate, get it to run, and you're done. Take a snapshot of that and get it, and you're done. So this one right here, and I know you're all ready to go in there immediately and start wiring this and get it to work. I want to tell you that there's a problem with this one, and the problem is this. For this one, we use the Siemens processors, the 30 models, and those are the oldest ones we have. Now they're starting to wear out. Just like me, they're starting to wear out. All right? There are 4 of them that are still good, as far as I know, and they're the ones that are out on the tables. The 4 that are off on the side tables, and I'll make sure that they're kind of tucked back away, are the ones that are not working, and I'll get rid of them and put them in another room or someplace so they're out of your reach. Okay? So the 4 that are still out will be the ones that are working. The 4 that are off someplace else are the old ones. We are going to replace these. These are going to be replaced with the same wiring, the same ball in the tube, but basically with a newer processor. But we just didn't get to this one. This semester was the worst. I started noticing them last semester, and this semester they're really getting bad. The reason is because they were bought in 2011 and 2012, And if you do the math, that's 14 years ago. And anytime you put a system together that goes for over 10 years, you're asking for trouble. And that's one of the reasons why you have jobs, because every 5 to 7 years, most people have to go through and work on their process and refurbish and take the old panel out and put a new panel, or take something out and put something in new, because things wear out, especially program controllers. After 7 years, most program controllers need to be replaced. Okay? They do, because they start to wear out. And these have been in there for 14 years. And guess what? They're wearing out. End of story. But you have 4 of them, they're still working pretty good. And all you gotta do is build a faceplate. Easy 8 points. I'm serious, it's an easy 8-pointer. But these are good labs. I've been told by the folk that did these labs a year ago that they took their auto controls course and they didn't understand SPIT, and they did 1 or 2 of these labs and they got a very good understanding of how the P, the I, and the D algorithms actually worked. So if you want to have a little bit of, like they say, meat on the bones as far as the auto controls course that you've taken or are taking now, and you want to know how they actually work, do one of these. And not only will you be able to walk out of here and say, I have programmed a PID block and a PLC, you'll be able to say, I understand how to tune a PID algorithm and actually be able to start it up and make it run. And that is worth its weight in gold, by the way, because most people, I was 20 years out of school before I actually did one. I was scared to death. But it's something, it's an experience. It's not like going to the 4th of July and firecrackers. It's not like that. But it's quite an experience to be able to say that you've done one of these. And it is another thing that you can check off that you've done. So again, I highly encourage you. One of the reasons we're moving this lab ahead is because this is one of the labs you can do. Doesn't take you more than an hour or 2 to get it done. And believe me, it does the job. Okay? Now this is the laser, the specifications for the laser that is at the top of this guy. And that laser, that's a laser up there. Please do not shine it in your eye. Please do not. And also make sure that it shines down the tube and hits the ball. If it doesn't hit the ball, the algorithm isn't going to, there's no algorithm that's going to work if you don't have a good feedback. And unless that laser hits that ball, it ain't going to work. Any questions about that lab? Okay. Now the other lab is this one. And these pictures are slightly dated, but this is a tank over another tank. Now here is your feedback device for your level control. So this is a level control in the upper tank, and what you're trying to do is you're trying to keep the level constant. So in the lower tank there is a there's the little motor controlling it. There is this thing. This is a pump. This is a bilge pump, okay? Now it runs on 24 volts. And it's supposed to run constant, but it doesn't. It runs on a pulse width modulated signal, okay? So this is a bilge pump. 24 volts. And it runs on a signal that is a pulse width modulated signal. That's called PWM signal, okay? Pulse width modulation means basically that's 24 volts at 0, 24 volts and 0. If you run it at half, you would run at about half speed. That's about half on and half off, and that would be approximately half speed. All right? 3/4 speed would be what? Like that. 1/4 speed would be what? Let me get it right here, Ted. Any questions about what pulse width modulation does? Okay. Now, the dark side of this is that pulse width modulation creates harmonics. And there's a capacitor in here, and the capacitor with harmonics will heat up. But because it's underwater, the water cools it, and usually it runs pretty well. If you run this thing dry, this thing gets hot. So please don't run it dry or run it very long. Don't sit there and run it for hours. Don't go to supper with this thing running at half speed, open, with no water in it, okay? Please don't do that. It'll burn it up. Any questions about some of the idiosyncrasies of our wonderful system? So that's another aside, but just in general, you don't do this unless you absolutely have to. They create harmonics. Any questions? So don't run it any more than you absolutely have to, and don't run it without water, at least some of the time on the motor, so it can cool it off. We had various signal devices we went through to get the level indication, but this was not working. This one actually did work. Worked well. And there it is. We had various devices that would give us a feedback of the flow from the bilge pump. So this is the first device, $10. Lasted about 10 minutes and then it broke. Then we got this, $110. Worked kind of well, but it didn't work well in the low range. Then we got this one, which is much better and works within all of our ranges. This one is kind of the same. What's the point of all this? You have to be careful how you buy these things, and more often than not, the more you pay, the better you get, but not always. But buy one, try it, see whether it works or not. This is not Go Fish. You have to read the specifications very carefully and then pick one and try it and see if it works. This is another project that I built, and we threw it away. We canned it. It's not around anymore. So it's kind of sad, but it's a nice analog system. Anyway, so that tank over tank is the other project that you can program. And you can do the same thing. The program exists. So you load program number 7 and then get, in that case, 2 HMI or two faceplates. But once you get one, the second one's not hard. Any questions so far? So this is some of the explanation of how that is set up and how it works. And then you have to start peeling away the layers. And there's some examples of the pulse width modulated signal. All right, so here are some of the, now that is the Germans always do things twice, where we could do things once, but there's their formula for the PID. You say, oh my goodness, yep, oh my goodness. So there is your proportional term, there's your integral term, and there's your derivative term. Which brings up another point. If you take your P, your I, and your D parameters from one PLC and move it to another competing brand of PLCs or PID algorithms, is it going to work? And the answer is probably not. Not well. It will work eventually, but not well. Okay, so what are some of the things you need to know about these in order to make them work? Well, for one thing, auto mode and both of these run on the Siemens PLC, and you probably will wonder, why don't you run these on the Allen Bradley? Well, I can't, because they don't have the same sophistication, that pulse width modulation. You have to pay a lot more money for Allen Bradley to get that than you do on the Siemens. So that's kind of like, Siemens is almost like an Arduino. They can do almost anything, and they do a decent job of it. Allen Bradley, you have to pay a lot more money to get that kind of capability. And so we've used the Siemens because they're a lot less expensive and they give you a lot more bang for your buck. But they do have some idiosyncrasies. This is a historical data plot. Now, if you are programming along and you want to see how your variable is responding, this is like an oscilloscope. This shows you the response of the signal to an input. Here is the PID block. They're already wired, you don't have to wire them. There's using the Allen Bradley. Same song set. This is for the one that was on the wall that we took down. By the way, one of the early days that we did this kind of stuff, when we had that valve on the wall, we attached the Allen Bradley and then we attached the Siemens processor to it, and we made that our lab. And I offered 5% of the course, offered a 5% increase for the person or group that did a YouTube video of their algorithm showing the algorithm for the PID algorithm on that processor. And the valve on the wall and the Siemens processor, the group that did that, the thing went viral. I mean, they had 30,000 hits within a very short period of time. And they may still be around. It was done in 2003 or 2000. No, it was 11, I think 2011 or 2012 when they did that. And one of the early examples of using an S7-1200 with the PID algorithm, and the guy that did that, his video went viral. So anyway, you want your video to go viral? That's one way to do it. Get in on the first floor and do it, and they did, and it worked very, very, very well. I don't know if he got paid. I don't know if he got into money or not, but anyway, it doesn't really matter. But that was then. Okay, so this is the Allen Bradley doing the same thing. Again, we don't have any Allen Bradleys. I'm sorry, we don't have, but this is how you would do it with them. Again, this is the setup page, the same page that you would have had with the Siemens. They both have the same process, the same things. So here is a canned faceplate from Allen Bradley. Okay, this would be one that you would just basically pull up from the Allen Bradley listing if you have the old factory talk. So this gets back into the older version of the graphic package that Allen Bradley had called Factory Talk, and pull up a PID faceplate and basically plop in the variables and watch them move. So this would be the arrow that would go up and down for it. It looks like a little moving arrow that goes up and down. So this would be your process variable. This is your set point, and you would actually see these go up and down. And then here's the set, if you want to do a set point, and this is the kind of stuff. This is the kind of thing that you would see, okay? And how to set them up. Very effective. And there is some more of the Allen Bradley stuff that you can do, which we can't do anymore. And here's how to set it up on the Factory Talk web page. This is their web page, how to set this faceplate up. Okay, animate. So if you do get into a situation where you're setting up an Allen Bradley process, some of this stuff is of value. There's 3 different types of faceplates that were done specifically for Allen Bradley. Now you say, do you want to see one like this, or do you want to see one like the original one that I showed you? I don't care, but I want to see a faceplate that has some of this stuff on it. Okay? Doesn't have to look exactly like this. What is it about this that looks kind of interesting? This has a 3D look to it, doesn't it? It looks like it's a 3D. It looks like this is actually etched in there, even though it's not. It's a flat surface, but they do the shadows to make it look like it's anodized aluminum and all that kind of stuff. And that's the way the original ones were done on a flat panel. So you'd have anodized aluminum. Everything looked really expensive because it was. Any questions so far? Okay. So now we get into the argument that you might or might not want to be a part of, but basically, how do you show a large number of PID algorithms? Well, you don't. You show the output and show what they're doing, and if they're okay, you don't do anything. But if they get out of range, what do? This one is in trouble, right? Because it's way up here and this is in the yellow range. In other words, it's starting to go south on you. What do? Here you have a what? You have an invisible button around this, which basically, if you click in this area, what does it do? It brings up another pop-up screen that allows you to change all the variables in this PID algorithm. Does that make sense? Because that's what you do. So you click on this or you click around this, there is an invisible button that basically brings up another screen. That invisible button, then you don't see it, but you basically, if you hover on this, there will be an outline of this, which basically says, if you click in this area, you're going to get a secondary screen. So basically, you click here, click here, click here, click here, and you will get a secondary screen over to the side. And what does that screen allow you to do? It allows you to do the faceplate. So basically, this is an overview screen. Everybody understand that this is just a bunch of PID algorithms all sitting there doing their thing, popping along, doing whatever. They're cool, they're good. Everything is copacetic, except for the fact that this one is starting to go out, right? So what do? Maybe nothing. Maybe it's been doing this for the last 3 years and you don't really care. Okay? It's like a check engine light coming on in your truck or your car. Sometimes you don't pay any attention because it's come on for like that for 3 years and it goes off. It comes back on, it goes off, comes back on, it goes off. Heck with it. Okay? But sometimes you really do want to take this into account and figure out what it's doing. So you click in this area and then a pop-up screen comes up and you start changing things like your P, the I, and your D, or you start looking to see what actually is going on. Does that make sense? Well, that's how that's done. So anyway, now here is that process that I did, okay? Now, so far, does anybody have any questions? Because we're getting close to the end. Does anybody have any questions? Because I'm going to finish off here in a few minutes and dismiss you. But does anybody have any questions about what I'm expecting for a lab from this? There's 2 8-point labs that I'll accept from Chapter 19. One is a faceplate with the ball and tube. The other one is 2 faceplates with the tank over tank, because there's 2 PID loops with the tank over tank. There's 1 PID loop with the ball and tube. So you can either do one, or you can do the other, or you can do them both. If you like this kind of stuff, I'll explain more on Wednesday night, but this is a career, by the way. You either walk into a company that basically is a pieces parts company, or is basically a process control company. This is dealing with process control. This is oil, gas, flow, anything having to do with flows or heat, that type of thing. So if you want to work in a company that basically does stuff that's continuous, flow type stuff, this is Chapter 19 is an opening to a career. Okay? You want to work for BP? Right here's your chapter. I mean, you can camp on this chapter to learn about this stuff. And if you do a PID algorithm, if you do 2 of them, you walk in and you talk to a recruiter, and they'll say, "What did you learn at the University of Toledo?" And you say, "Well, I did this PLC course." And they say, "Okay, that's nothing that we ever do." You say, "Well, I didn't. I programmed 2 PID algorithms, and I got this thing to work for a ball and a tube and a levitated ball and tube, and the other one I did a loop within a loop." They'll look at you and say it again, because they don't believe you. They don't believe that you've actually done two different ones. This is an example of something that you can increase your viability by leaps and bounds, because most people don't do this. They don't have actual things you can get your hands on and actually, you know what I'm saying? Actually get your hands on and actually do and actually program and make it work. And this is the chance that you have to do that. So I'm not begging you to. But if it's at all something you want to do, this is, that lab 2 was to get you started with the pieces parts, the lab where you did the relays and all that kind of stuff. That was to kind of introduce you to the pieces and parts algorithms, the seal circuit, all that kind of stuff. This is your one shot at the other side of the coin, which is a process, which is flows, keeping everything nice and even, everything, nice flows. Okay? You say, well, I want to work in automotive, and they'll never do this in automotive. They do. The paint room is nothing but PID algorithms. Okay? Nothing but. So if you want to work in a paint room at a automotive facility, this is all you'd get, is PID. But this was the algorithm that I was asked to do with the that one PID algorithm at the Andersons. They were adding fat to the dog food. This is the whole process. There's an extruder motor, and they were basically putting all the ingredients in through the top, feeding them in, and they were like a bread dough mixer. They were doing this, and there was steam coming in from the side, and out the back come kibbles and bits. And they wanted to add fat. So if they're moving this motor, this DC motor, this big fat old DC motor faster, they're making more kibbles and bits. If they're moving it slower, they're making less. These went into bags, by the way. They bagged this immediately. So if you wanted to go faster, you would add more fat. If you wanted to add slower, you'd add less fat. So this was a follower to this. Does everybody see that? As this speeded up, this would speed up. As this slowed down, this would slow down. They wanted to be able to dial in from 2 to 5% fat for the amount of kibbles and bits they were making. So you can say 2, 2.1, 2.2, 2.3, up to whatever. And then it basically multiplied by this number, and then that gave you a percent of flow. That's all it was. That's the one that I had to call a friend on in order to figure out how the middle parameter, the proportional, the integral parameter worked, as small as big. So anyway, so this is how most processes work. You have a master, and then the boss says, I want to make more today. You turn that puppy up, and everybody follows. If you want to make less today, we don't have as many orders, you turn the speed down, and you make less. This is the master, and everything follows. This is called cascade, or a follower system, or a cascaded system. That's how that's done. Okay? Now this is how the algorithm works for a auto and manual. If you're an auto, you follow through the algorithm, and basically you go through this way of going. And you either are in the local set point or you're in the cascade or remote set point. So you pick one or the other. Now, if you are in manual, you do not go through the algorithm. You go over to this position and you actually control the output valve. You have your hand on the valve. You control the valve with your hand as opposed to letting the algorithm control the valve. Okay? Now, why would you ever go to manual? Other than when you start up. When you first start up, you have to establish the output before you can establish the input. Does everybody follow that? You have to turn the output on before you can even get an input signal to come back and verify that it's even on. So you have to be in manual when you first start up. You have to. You can't start up in auto. Well, don't say can't, but you probably don't want to start up in auto. You want to start up in manual because you want to see this signal. You want to verify that the signal is there. So you start up in manual. You turn this valve to a certain position. You want to see a certain feedback coming back, and that's how you get started up. But why would we ever go to manual after we've started it up in the original position? Well, the case comes up that you have if I were to come back up here, and there was a rag that came down through this thing and plopped into this valve, what would happen to that valve? It would plug up, I guarantee you, okay? The old rag in the valve trick. So that would be you would go to zero flow, or very close to zero flow. Now, what happens when that happens? If you stay in auto, what happens? What happens to the integral of the error? It gets bigger and 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 bigger. And you want me to shut up eventually, I will. But it gets bigger and bigger and bigger and bigger and bigger. Now, when that rag flushes through, what happens to that valve? What happens to that valve? It takes forever for that integral of that error term to come back to 0. It takes it forever. So what do you typically want to do? If something bad happens, you want to go back to a safe mode. In the case of the integral of the error term, what do you want to do? You want to go back to manual, because what happens in manual is you kill the integral of the error term. You kill it. It goes to 0. So if you go to manual, this algorithm stops working, and if you go back to auto, what happens? You start from 0 with the integral of the error term. It starts from 0 again, it starts going again in normal. It starts back at normal. So if you have a problem, you want to wait where you're at, stick where you're at, most of the time stay exactly where you're at, and then when you get back, pick up from there and keep going. Another case in point, this will be my last. When a valve is turning to try to control the flow of gas into a furnace, okay? That turning of that motor that does that turning, there's a linkage between the motor and the actual valve. All right, that linkage is a mechanical linkage. If a linkage comes loose, what happens? You turn, but it doesn't respond. So you put a potentiometer on the valve and you turn, and if it doesn't respond, what do? You stick in manual, because you do not want to, you want to stay where you're at, and you don't want the integral of the error term to start building up. And what else do? You tell an operator to get a maintenance person to go fix the linkage. And when they do, and they get it fixed, then you go back into auto, and you're back in business. So does everybody see the progress? You fall back. You fall back to a defensive position that allows you to continue running your process without error, or close to without error as you can. You fall back to a safe position, and then you keep going from that point on. Isn't this fun? But that gives you some ideas. Hopefully some of this stuff sticks. And we're about 2/3 of the way through this chapter. Now, this will be done in another night. But I want you to understand that you now have enough in your tool house to be able to do those 2 labs. And I want you to try them, because they are you have to sling water with the one. You have to physically put a 5-gallon bucket of water in the upper chamber in order to get it to work. You don't do that right away. You have to set your calibration and follow through the lab that's there. Do that, and then elevate it by putting in a faceplate. If you have any questions, see me when you're ready, and I'll help you. You'll have fun. Slinging the water is a lot of fun, and then you got to drain it and all that kind of stuff. But it's not a bad lab, and they're very, 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 very good labs to be able to say that you've done. Okay, did everything make it around? Did everybody get what they wanted? Any questions anybody has? Have a good evening. Take care.
So we go down